that's going on, and you just, it's like astrology. You know, people believe in astrology, people believe in phrenology, people believe in palmistry, people believe in random people telling you of your future. Why are they still there? They're bosonists, right? And basically, if anybody ever did systematic study, you can prove that they're useless. Nobody ever does systematic study. People give it a point whenever it comes up true, and don't count it when it doesn't come true. If you do that, everything is a good idea. Do you understand what I'm saying? If you don't use scientific method, everything is a good idea. And it's the same thing for neural networks. You are basically giving them benefit when they wind up being correct on the test examples. But if I can make infinite number of new test examples that are all school buses, but your neural network calls it ostriches, what are you celebrating? Do you see what I'm saying? So we basically started from a simple goal of doing something like fitting some kind of a parameterized representation for reinforcement learning, the value function. And unbeknownst to us, we just devolved into this much larger problem of generalization and about all sorts of interesting things like bias variance trade-off and overfitting, and but does it happen, does it not happen? All of this you want to keep in your mind as we go through this class as well as the next 2-3 classes. In fact, for the rest of your life. Okay, because these are very important things. Okay, now the next thing of course is, so I'm still kind of coming back to reinforcement learning. You have these values, right? The current estimate of the values. You want to somehow fit a parametric function to this. Right? So I can do it in 3 different ways. One is I can consider, actually one is here. I can consider the current set of values for all the states, which gives me in the n-dimensional space, assume that all states are represented by k features. So in this k-dimensional space, each state is a point, right? And then the value would basically be, in that space, is the value of that state. Okay? And then I'm trying to compress this. I'm trying to basically generalize, find a parametric. If I do this, then essentially I'm looking at a huge number of examples first, and then deciding how to set the weights. This would be called offline learning. That means you want to see all the states and their values, then I will convert it into some parametric form. It becomes much closer to compression. But in reinforcement learning, actually, there is this other thing that you're a lot more interested in, which is as the agent is behaving in the world, it's updating its values. Right? As it is behaving in the world, it's updating its values. Before, the value became from 17 to 19, because it was connected to a good state. Now, the weights, the Wi that are used to compute Wi times Fi, summation, those weights are changed. So for every change in the value, every time I see an example, I change the weights. This would be incremental. Every time I see a new example, I change my learned generalization. Do you see what I'm saying? That would be called online learning. And this is offline. And in between is this batch learning, where you might say, I'll wait for, after seeing about 15 states changing their values. Now enough things have changed, so I will refit to these new states and values. That's 15 is a batch, RNA batch. Okay? Now it turns out that in normal generalization, all 3 approaches are reasonable. In fact, most people start with this. If I tell you all the students and their grades up front, right, then you will try to find a pattern with that data, and then you start applying them to new students. Okay? But in the case of reinforcement learning, actually, online methods are a lot more suitable. Because this way, as the agent is behaving, it is doing 2 kinds of learning. One it's doing temporal difference learning, the other it is doing generalization learning. Both at the same time. You see what I'm saying? So that's what we will do in today, and we'll show you some points about this, and we'll get back to it next class again. So, by the way, the only difference is I basically call them WI, W1, W2, etc. But this one, people tend to use thetas because that's a more sophisticated way of talking about weights. So the more Greek letters you use, the more mathematical you sound. So in fact, you go to Greece, you think they're all completely mathematically oriented. They used to be when Socrates was alive, but of late not so much because have you seen their budget? Right? Anyway, so I basically am taking this S, I'm trying to fit the value of the state S in terms of this theta vector, the W, weight vector. Okay? So the question, of course, is how do if I started with some initialization of the theta values in the beginning, and then I started doing TD, and when the first transition occurs, I now know that according to my original, if I start with initialization of theta values, every state has an initial value. After the first transition, you have a better understanding of the state's value based on its neighbors. You want to change the thetas such that the number that comes out is closer to the nudged number. Do you guys see that? You don't get to just change 17 to 19. You have to play with the thetas such that it comes closer to 19. Do you understand what I'm saying? So imagine I have a favorite in this class. I've told you that there is a linear function that defines your grade. W1 times homework, W2 times blah, blah, etc. And then I somehow want one particular favorite or particularly non-favorite person, I have more of those, to not get a good grade. Do you see what I'm saying? I could just always say, everybody else follows this formula, you get a C. That won't be good because then the provost will call me and say, Rao, are you starting to kind of, be very rude to people specifically? It's okay to be rude to a whole bunch of people. For individuals, it's not good. Okay? So what you need to do then, what I need to do now is to change the weights such that the guy that I don't like will wind up falling below the threshold. You see what I'm saying? He will fall, he or she will fall below the threshold. But the problem now is while that guy's grade is changed, so did everybody else's grade. Is that a bug or a feature? Did you just understand what I said? So I was trying to basically change the weight such that some person will get a specific grade, which is like changing the weight such that this guy's value becomes 19 instead of 17. I will make that. But then whatever I make here is going to affect everybody else's value too, because they're all using the same features and they're using the same weights. Of course, you can say everybody gets a different set of weights, which is a beautiful way of saying I decide what your grade is. I know that. Throw the semester out, I just toss a coin and give you a grade. You see what I'm saying? That's not what we do. We assume that there's a single function. That's the valuation of every state in terms of its features. And so when you change the values of one state, you wind up changing everybody's value. And that can be seen as a bug or a feature. In fact, here we will see it as a feature. Because you would say, look, you learned that everybody who is of this kind of features, this is what we are doing in this Pacman case. So if this guy's value has been improved, nudged, and if these guys are similar in feature space, even though they are not similar in the picture space, their values also will improve. I say, good. Whenever it works, I take credit. And it doesn't work, I say, it's machine learning, what do you expect? No miracles. You see what I'm saying? That's basically what we're going to do. So we're going to just figure out how to nudge thetas. How to nudge thetas such that a 17 becomes a 19. So this is where, essentially, of course, you realize that there's the two big switches we did. One is we already noticed that we are no longer in the atomic states, we are in the lifted states. And the second is we are going to be searching for these thetas such that they would be the best set of weight values that will bring this guy closer to 90 from 70. So that's like a search for weight values. You could use a star search and you'll die. Why? Because weight vector is a real valued vector. There are infinite number of dense reals. Dense not in the sense of dumb, but dense in the sense of there's in every little interval that you can take, there are infinite number of reals in that interval again. Integers are not dense, they're small, and real numbers are dense. And real valued vectors are basically dense. So you can't search by systematic search. So you appeal to function minimization. The only search available in continuous value spaces is your calculus. You look for the maxima or minima of a certain function. So the question then, I'll skip over this, and then basically you do know that the way to get to the maxima or minima of a function is to take the partial derivatives. If it's a normal, if in the simplest case, in your AP exams, you were given a function, you will take, it will be a single variable function oftentimes, you will take the derivative of it, it will be an analytical expression, you equate it to 0, you solve the equation. But if the equation that I give you happens to be a transcendental equation or a 15th order polynomial equation, you say, I don't know how to solve this. Do you understand what I'm saying? Only we know how to solve linear equations. Sometimes quadratic equations. Maybe once in a while cubic equations. Abel told us how to solve the 5th order equations. That's about it, guys. Everything else we don't know how to solve. If you set this thing to 0, what should be the value of x? You don't know. What should be the value of the point? You don't know. So there is another idea which actually calculus tells you that if you were to take the derivative, instead of setting it to 0, you actually take the value of the derivative, the actual value, not the analytical expression, the actual value of the derivative at that point. That would be a vector. Gradient is a vector. It's a vector, if it's a k-dimensional space, there's a k-dimensional vector of partial derivatives. That vector tells you, vectors look like this with an arrow in any space, and they tell you which direction you should move to increase the function's value. If you're trying to maximize the function, the best idea you can do is move in the direction of the derivative. You might say, hey, what if now it goes up and then comes down and then goes much higher up? And I say, yeah, that's what happens. Nobody ever told you that continuous search has optimality guarantees. A star search has optimality guarantees. Continuous search does not have optimality guarantees. You can find the closest maximum or closest minimum. And then you hope, like Columbus did, that what I found is the maximum. Remember that Columbus was looking for India. And his map told him that between Europe and India, there is huge amount of ocean. Because the quote-unquote Native Americans who were here, nobody thought they were there. And so he kept going and hit landmass and he said, must be India. So let's call all the people here Indians. In fact, at that time, Indians were in India, the other India. You see what I'm saying? It's the same thing gradient descent does. If you don't have map and you do local search, then you get to a point where derivative becomes 0. They say, I declare by powers granted to me by Queen Isabella or whatever, I declare this is the global maximum. And you want to prove me wrong? Find another one. And it will be a while after, Columbus's celebrations are over that people find that he was a bozo. That in fact there is more stuff to the map. This is what local search is. One last thing I want to do before you go off is actually this connection. This is again a calculus connection. Okay, it's kind of worthwhile thinking about, which is the whole gradient descent. Basically, the idea that I was making the previous thing is if you make a small step in the direction of the gradient, you go towards the maximum. If you make a small step in the negative direction from the gradient, you make a step towards the minimum. The size of the step is alpha, which is some arbitrary constant you figure out. If you don't know what the constant should be, you call it hyperparameter, because calling it fudge factor looks bad. Okay? Now, I want to tell you that Newton-Raphson method exists, which is something that you may have heard about. How many of you heard about Newton-Raphson method? It's the way you find the roots of any function. That is a zero crossing of any function. That's a very simple idea. So here is this function g. Okay? And I'm at x here. So this will be g of x. If I draw a nice tangent here, and you see where the tangent hits x-axis, you know that this will be closer to the zero crossing. You see this? In this picture at least it's true. Right? So now the question of course is, if I'm starting from x, I want to reduce x towards this direction. How much? By this much. What is this delta? This delta is nothing but g of x. This delta is basically the run, and g of x by that, so g of x by delta is equal to g dash of x. Because remember, derivative is the slope of the line. Slope is rise by run. So if I want delta from this, then delta is equal to g of x by g dash of x. So I start with an x, any arbitrary x, subtract from x g of x by g dash of x. I'll get a new value for x. And you keep doing this, you will very nicely get to the zero. Okay? Now, if you see this is Newton-Raphson method, and if you realize that finding a maximum is finding the zero for f dash, so everything will have an extra dash. So previously you're finding the zero crossing for g. Now you're finding zero crossing for g dash. So if you want to just apply Newton-Raphson for this, it will be x minus f dash x by f double dash x. If you do this, this is the amount of time, the amount of distance that you have to move towards the zero crossing. Notice that because of the way the slope would be, you will be able to move any direction, the correct direction. And notice that there is no fudge factor. What is the fudge factor here? It's in terms of f double dash. Because you are essentially moving in the direction of f dash, but you are dividing it by f double dash. So 1 by f double dash is the fudge factor. If you do this, then you don't need fudge factors. If you can do this, then this is the definition of optimization of continuous functions. There's a huge problem. The huge problem is for the single variable functions, f dash x is a scalar, f dash x, and f double dash x is also a scalar. For two variable functions, f dash x is a gradient of two elements, f double dash x is a matrix of four elements. For n variable function, a gradient is n element vector, and this basically the double dash is going to be n square elements. How many of you have seen Liberty Kids while growing up in this country? That's a picture of Hessians. Hessians are connected to the US freedom struggle. The Germans came and helped. Um, this is called Hessian. The second order derivative matrix is called Hessian. If you can deal with Hessians, then you already have a way of minimizing or maximizing a function without any additional fudge factors. Turns out Hessians are too hard to handle, so you find methods like alpha or momentum based method that we'll talk about, or atom which we'll talk about, etc., which are all things that try to get to what should have been possible.